Induction motor, principle of operation and the torque speed curve. Three-phase induction motors are simple, rugged, low-priced and easy to maintain. They are commonly used in building services systems. In this animation, we will introduce the principle of operation and then the torque speed curve. A three-phase induction motor has two main parts, a stationary stator and a revolving rotor. The stator consists of a steel frame that supports a hollow cylindrical core made up of stacked laminations. A number of evenly spaced slots punch out of the internal circumference of the laminations provide the space for the stator winding. The rotor is also composed of punched laminations. These are carefully stacked to create a series of rotor slots that provide space for the rotor winding. The squirrel cage rotor is composed of bare copper bars, slightly longer than the rotor, which are pushed into the slots. The opposite ends are welded so that all the bars are short-circuited together. The entire construction resembles a squirrel cage, from which the name is derived. When a three-phase AC current passes through the stator winding, it produces a magnetic field that rotates in time with the AC oscillations and penetrates the rotor. The rotor will start to rotate in the direction of the rotating stator magnetic field based upon the application of Faraday's law and the Lorentz force on a conductor. Faraday's law of induction is a basic law of electromagnetism and predicts how a magnetic field will interact with an electric circuit to produce an electromotive force, or EMF. It is the fundamental operating principle of induction motors. In 1831, Michael Faraday discovered that any change in the magnetic environment of a coil of wire will cause an EMF to be induced in the coil. Faraday's law states that the magnitude of the induced EMF in a conductor is directly proportional to the time rate of change of magnetic flux through the conductor. In other words, EMF is proportional to delta phi divided by delta t. Lenz's law is a qualitative law that refers to the direction of induced current in relation to the effect which produces it, without quantitatively relating their magnitudes. It states that the direction of the induced current will always oppose the inducing action of a moving magnet. When a current-carrying conductor is placed in a magnetic field, it is subjected to a force called the electromagnetic force, or Lorentz force. The magnitude of the force depends upon the orientation of the conductor with respect to the direction of the field. The force is greatest when the conductor is perpendicular to the field and zero when it is parallel to it. Between these two extremes, the force has intermediate values. The direction of the electromagnetic force can be illustrated by Fleming's left-hand rule. When an electric current passes through a solenoid, it produces a magnetic field. The right-hand grip rule states that if you wrap your right hand around the solenoid with your fingers in the direction of the conventional current, your thumb will point in the direction of the magnetic North Pole. To understand the operation principle of an induction motor, let's consider the stator as a series of conductors whose ends are short-circuited by two bars. A permanent magnet placed above this conducting ladder moves rapidly to the right so that its magnetic field sweeps across the conductors. A voltage is induced in each conductor while it is being cut by the flux due to Faraday's law. The induced voltage immediately produces a current which flows down the conductor, below the magnet, through the end bars and back through the other conductors. Because the current-carrying conductor lies in the magnetic field of the permanent magnet, it experiences a mechanical force known as the Lorentz force. The force always acts in a direction to drag the conductor along with the movement of the magnetic field. If the conducting ladder is free to move, it will accelerate towards the right. However, as the conductor ladder picks up speed, the conductors will be cut less rapidly by the moving magnet, with the result that the induced voltage and the current will diminish. Consequently, the force acting on the conductors will also decrease. In an induction motor, the ladder is curved to form a squirrel cage, and the moving magnet is replaced by a rotating field. The field is produced by the three-phase currents that flow in the stator windings. The animation now explains the rotating stator magnetic field. Consider a simple stator having three pairs of coils which are equally spaced. Two sets of coils in the same pair are diametrically opposite and are connected in series. This creates three identical sets of windings that are mechanically spaced at 120 degrees relative to each other. If we supply a three-phase source to the three windings, the currents in the three windings will have the same value, but will be displaced in time by an angle of 120 degrees. During the positive half cycle of the R phase, the current will flow in this direction along these two windings. According to the right-hand rule, the magnetic flux is in the direction shown, creating north and south poles. In the negative half cycle, current will be flowing in the opposite direction. Therefore, the flux lines will also be in the opposite direction. For the Y phase during the positive and negative half cycles, the flux lines will be in these directions. For the B phase during the positive and negative half cycles, the flux lines will be in these directions. The magnitude of the flux is directionally proportional to that of the current. As the current varies with time, the magnetic fluxes created by the three phases will vary accordingly as shown. As flux lines can't cross each other, the three fluxes combine and produce a magnetic field having essentially one broad north pole and one broad south pole. This means this stator produces a two-pole field. The magnetic field rotates with time and makes one complete turn in one cycle of current flow. The rotational speed of the field depends therefore upon the duration of one cycle or the frequency of the source and the number of pole pairs. Because the speed of the rotating field is necessarily synchronized with the frequency of the source, it is called synchronous speed. If the frequency is 50 Hz, the resulting field makes one turn in 1/50th of a second, that is 3000 revolutions per minute. The synchronous speed can be reduced by increasing the number of pole pairs. A rotating magnetic field is created in the stator with the same frequency as the source. With the rotor locked, the rotating field cuts across the rotor bars and induces a voltage in all of them. Because the rotor bars are short-circuited by the end-rings, the induced voltage causes a large current to flow. The current-carrying conductors are in the path of the flux created by the stator. Consequently, they all experience a strong mechanical force. The sum of the mechanical forces on all the rotor bars produces a torque which tends to drag the rotor along in the same direction as the revolving field. As soon as the rotor is released, it rapidly accelerates in the direction of the rotating field. As it picks up speed, the relative velocity of the field with respect to the rotor diminishes progressively. This causes both the magnitude and the frequency of the induced voltage to decrease because the rotor bars are cut at a slower rate. As the rotor speeds up, it never manages to catch up with the revolving field. If the rotor did turn at the same speed as the field, the flux would no longer cut the rotor bars and the induced voltage and current would fall to zero. Under these conditions, the force acting on the rotor bars would also become zero, and friction and windage would immediately cause the rotor to slow down. The rotor speed is always slightly less than the synchronous speed in order to produce a current in the rotor bars sufficiently large enough to overcome the braking torque. The difference between the synchronous speed and the rotor speed, expressed as a percentage of synchronous speed, is called the slip S. The torque developed by a motor depends upon its speed. Their relationship cannot be expressed by a simple equation. Instead, a torque-speed curve is usually used to show the relationship. When a motor starts to rotate from rest, a locked rotor torque or breakaway torque is developed. It is usually larger than the full load torque. As the motor starts up, the torque reduces slightly until the pull-up torque is developed as the motor speeds up. The torque continues to increase to the breakdown torque as the motor runs faster and faster. This is the peak torque that can be developed by the motor. As the motor goes through the breakdown torque and its speed continues to increase, the torque drops. As the rotor speed approaches the synchronous speed, the torque becomes zero. If a mechanical load is now applied to the shaft, the motor will begin to slow down and the revolving field will cut the rotor bars at a higher and higher rate. The induced voltage and the resulting current in the rotor bars will increase progressively, producing a greater and greater motor torque. The motor speed will cease to drop when the motor torque is exactly equal to the road torque. The motor and the mechanical load now reach a state of equilibrium and the motor will turn at a constant speed. If the mechanical load increases, the speed will drop until the motor torque is again equal to the load torque. As soon as the two torques are in balance, the motor will turn at a constant but lower speed. However, if the load torque exceeds the breakdown torque, the motor will quickly stop. In real applications, various kinds of loads exist with different torque speed curves. For example, constant torque variable speed load, variable torque variable speed load, constant power load, constant power constant torque load, and high starting torque followed by constant torque load. As mentioned previously, the motor will turn at a constant speed when the developed motor torque is equal to the load torque requirement. Apart from that, the motor load system can only be termed stable when the operation will be restored after a small departure from the equilibrium point caused by a disturbance in the motor or load. A motor with a torque speed curve shown in red is driving a load which has a load torque curve shown in green. The motor is working at the operation point. Disturbance to the motor system causes a reduction in speed. At lower speeds, the motor torque is greater than the load torque. Consequently, the motor will accelerate and the operation will be restored to the operation point. Similarly, an increase in speed caused by disturbance will make the load torque greater than the motor torque, resulting in a deceleration and restoration of the operation point. Hence, the system is stable. A suitable motor should be selected for driving the given load. Various standards exist which specify various operating and constructional parameters of motors. One of the most widely used standards are those of the National Electrical Manufacturers Association, or NEMA. The Nema Standards mainly specify 4 design types of AC induction motors, designs A, B, C and D. Design A has normal starting torque and relatively high starting current. The breakdown torque is the highest of all the NEMA types. It can handle heavy overloads for a short duration. A typical application is the powering of injection molding machines. Design B is the most common type of AC induction motor sold. It has normal starting torque, similar to Design A, but offers low starting current. The motor efficiency and full load power factor are comparatively higher, contributing to the popularity of the design. Typical applications include pumps, fans, and machine tools. Design C has high starting torque, useful for driving heavy breakaway loads like conveyors, crushers, stirring machines, agitators, reciprocating pumps, compressors, etc. These motors are intended for operation near full speed without great overloads. Design D has high starting torque, higher than the other NEMA motor types. The starting current and full load speed are low. These motors are suitable for applications with changing loads and subsequent sharp changes in motor speed. The speed regulation is poor, making the design suitable only for punch presses, cranes, elevators and oil well pumps.